Hello everyone, welcome back to our channel Alchemist. Today we are going to see the F block elements. As already we completed the S block, B block and D block, now we are going to see the F block elements. Let's get into the video. And now we are going to see the location, that is location of F block elements. See this periodic table, as already we know this is S block and this is P block, this is D block and this is F block, okay. That is the two series, the lanthanide series and actinide series are known as F block elements. It is actually placed at the bottom of the periodic table, but it is not separated from the periodic table, okay. And lanthanide series is a subset of 6th period and actinide series is a subset of 7th period, okay. This is in the 2D form, so they kept at the bottom. And now see this periodic table, this is in 3D form. It is not separated, it is at the back side of the periodic table, okay. And these are the differences between 2D and 3D form, okay. Actually in 3D form it is like this. I think now you got a better understanding. Okay, next slide. And now we are going to see the F block elements in detail, okay. First we are going to see what are F block elements. F block elements are elements whose F orbitals getting filled up by electrons is known as F block, okay. And then there are 14 electrons, okay, 0 to 14 in F orbital and 0 to 1 in D orbital, that is the penultimate shell. And then in outermost orbital, that is S, consists of 2 electrons. And then we know that there are two series in F block, as already we know that the 4F series and the 5F series, and we know that there are 14 elements get filled in the F orbital in each series. So in lanthanide series there are 14 elements and in actinide series there are 14 elements, okay. And now we are going to see the classification of F block elements, okay. And as we know that there are two series in F block, they are lanthanides and actinides, as we already know. And now we are going to see the classifications. As we know that in lanthanide series there are 14 elements starting from lanthanum to lutetium, okay. And the atomic number starts from 57 to 71, okay. The name lanthanides fall on the element lanthanum because they arrived immediately after lanthanum. So it is known as lanthanide series, okay. And then the second one is actinide series, and it starts from actinium to lawrencium, and there are 14 elements in actinide series, and it starts from the atomic number 89 to 103, okay. These are the basic classification of F block elements. Okay, now we are going to see the elements present in F block, okay. And we saw in the earlier slide that there are two series, that is lanthanide and actinide series, and these are the two series of elements, okay. And then now we are going to see the names of these two series, okay. First we are going to see the lanthanide series. The first element is lanthanum, its symbol is La and its atomic number is 57. And then cerium, Ce and 58. Oh, and then praseodymium, it is Pr and 59. And then neodymium, Nd and 60. Promethium, Pm 61. Samarium, Sm 62. Europium, EU 63. And then gadolinium, it's GD, it's wrongly marked, and 64. Terbium, it is TB 65. And dysprosium, that is DY 66. And then erbium, it is ER 68. And then thulium, it is TM 69. And then ytterbium, YB 70. And then lutetium, Lu 71. These are the elements of lanthanides, okay. And then we move to actinide series, okay. And the first element is actinium, its symbol is AC, and its atomic number, Z means atomic number, okay, it's 89. And then thorium, TH, its atomic number is 90. And then proactinium, it's Pa91, uranium it's U92, neptunium Np93, plutonium Pu94, americium Am95, curium Cm96, berkelium Bk97, californium Cf98, einsteinium Es99, fermium F100, mendelevium Md101, and nobelium NO102, lawrencium. This is the last element of actinide series, Ella 103. Okay, these are the elements of actinide series, and these are the elements present in F block. Okay. Why F block elements is known as inner transition elements. Okay, and we know that we call D block elements as transition elements, and as we know that location of F block is it lies much inside than D orbital or D block. Okay, so it is known as inner transition elements. And then what are the properties of F block? The first property is it have electrons added to f orbital in n minus 2 level. When we see electronic configuration, it consists of that is the noble gas family like xenon, krypton, etc. And then f orbital, d orbital, and s orbital. Okay, in f that is n minus 2 level, and in d n minus 1 level, and yes it is ns block elements. Okay, ns, and it have properties similar to D block elements. Okay, because F block or the subset of sixth and seventh period, as we know. So the properties are very close or similar to each other. Okay, and now we are going to see the trends, that is lanthanide contraction. Okay, the steady decrease in the size of atoms and ions of the rarest elements, that is F block elements, with increase in atomic number. Okay, the size decreases and the atomic number increases on moving from lanthanum to lutetium. Okay, this is known as lanthanide contraction. And let's see the causes of lanthanide contraction. Okay, and it is caused by a poor shielding effect of 4f electrons. Okay, as we know that lanthanide series is 4f series, so poor shielding of 4f electrons. And the next one is when we move from cerium to lutetium, the nuclear charge increases, okay, by 1 unit, and an additional electron is added to the same inner 4f section. When nuclear charge increases, an electron added in the 4f section. Okay, and then we know that the shielding effect of 4f electrons is relatively very poor. Okay, and with increase in nuclear charge, the valence shell is pulled slightly towards the nucleus. Okay, and then the effective nuclear charge experienced with 4f electrons increases and the size of Ln3 plus ions decreases. This means the steady decrease in the size of atoms or ions with increase in atomic number. Okay, the atomic number increases and the size of the atoms decreases. This is known as lanthanide contraction. Okay, and what are the consequences of the lanthanide contraction? There is a basicity difference, that is when we move from cerium to lutetium, the basic character of Ln3 plus, that is decreases. Okay, as we know there is a steady decrease in the size of the atom or ion with increase in atomic number. Okay, so the ionic character, that is LNOH bond, that decreases, and the covalent character increases. Okay, and which results in the decrease in basicity. Okay, this is the important consequence. And then the next one is hard to separate the lanthanides. It is very hard to separate the lanthanides, and increase in electronegativity and increase in ionization energy, and decreases the ability to form complex. Okay, and then the next one we are going to see is the actinide contraction. That is, it is same like lanthanide contraction. When a size of the atom or ion decreases with increase in atomic number in pi f, that is the causes is it poor shielding of pi f electrons. Okay, so larger is the contraction along the period. Okay, And now we are going to see the electronic configuration of F block elements. Okay, first we are going to see the general electronic configuration. This is the general electronic configuration, that is n minus 2, F1 to 14, n minus 1, D0 to 1 and ns2. Okay, and now we are going to see the general electronic configuration for lanthanides, that is xenon 4 of 14, 4 of 1 to 14, 5d0 to 1 and 6s2. And then the general electronic configuration for actinides, it's radon 5 of 14, 6d0 to 1, 7s2. Okay, and let's see them in detail. Okay, for lanthanides and actinides. Okay, now we are going to see the electronic configuration of lanthanides. Okay, and the general electronic configuration of lanthanides is xenon 4 of 1 to 14, 5d0 to 1, 6s2. Okay, and then this already we know. In lanthanides, the electron enters to the 4f orbital. That is, in lanthanum, the 4f is 0. Okay, and then in from cesium to lutetium, the 4f orbital increases. That is, the electron comes to the 4f orbital when atomic number increases. Okay, and see this. These are the elements of 4f, that is 4f series or lanthanide series, and these are the electronic configuration. Okay, and if you notice, the 4f increases by 1 unit. Okay, 1 3 4 5 6 7 9 10 11 12 13 and 14. Okay, if you notice, in lanthanum, gadolinium and lutetium, they are completely filled or half-filled configuration they have, so it is more stable than other elements. Okay, and the electronic configuration for actinides. Okay, and we know that there's a general electronic configuration, and in this actinides, the electron enters to 5f orbital, and these are usually, we know that in actinium, 5f0. Okay, and the electron enters to thorium to lawrencium. Okay, and then if you notice, in actinium and then curium and lawrencium, they have completely filled or half filled subshells. Okay, they are more stable than other compounds. If you notice, the electrons increases 1 2 3 4 6 7 9 10 11 12 13 14. Okay, in 5f only, other remains same. Okay, and now we are going to see the general characteristics of F block elements. Okay, the first one are, they are usually heavy metals. Okay, as we know that the atomic number increases, the metal's weight also increases. Then the next one is, these elements have higher melting and boiling point. And then the third one is, they display a variety of oxidation state. Okay, and these elements tend to form colored ions. Okay, and then they form complex compounds. And the next one, we are going to see the oxidation state of F block elements. Okay, and this is the lanthanide series, and these are the oxidation state. The common oxidation state is +3. Okay, and for we know that F block elements exhibit variable oxidation state, and some elements show variable oxidation state. Okay, but the common oxidation state is +3, and this is actinide series. Okay, and the common oxidation state in actinide series is also +3, and some show variable oxidation state. Please note it. And then the properties of lanthanide series. In lanthanides, they have soft metals with silvery white color, and then their color dulls and their brightness reduces rapidly when exposed to air. If we expose to air, the color will become dull. Okay, due to air. And then they have melting point ranging from 1000 Kelvin to 1200 Kelvin, except samarium. Okay, it has 1623 Kelvin. And then Lanthanides are good conductors of heat and electricity. As we know, metals are good conductors of heat and electricity. And then they are non-radioactive in nature except chromium. Chromium is a radioactive metal. And then we know that lanthanide contraction, that is a steady decrease in the atomic or ionic radius when increase in atomic number is known as lanthanide contraction. Okay, if we notice lanthanide contraction in lanthanum to lutetium, in this the atomic number increases and there is a steady decrease in the ionic or atomic radius. Okay, and now we are going to see the properties of actinide series. The first point is they appear to be silvery in color, and then these elements are radioactive. They are fully radioactive elements, and these metals are highly reactive, and the reactivity increases when they are finely divided. And then, as we saw in lanthanide contraction, in this actinide contraction occurs, that is the same like lanthanide contraction, a steady decrease in atomic or ionic radius with increase in atomic number from actinium to lawrencium is known as actinide contraction. And then we know that we saw in the earlier slide, that is the oxidation status, common oxidation status plus 3, and elements belonging to the first half exhibit variable oxidation state, and the uh, next half exhibit the common oxidation state, that is plus 3. Okay, now we are going to see the differences between lanthanides and actinides, and these are the differences. The first point is binding energies. Okay, the binding energies of 4f electrons are higher and the binding energies of 5f electrons are lower. Okay, and the second point is maximum oxidation state exhibited by lanthanides is plus 4, for example Ce4 plus. As we already discussed, the binding energies of 5f electrons are lower, so due to lower binding energy, they show higher oxidation state, that such as plus 4, plus 5 and plus 6. Uranium exhibits plus 6 oxidation state in UF6 and UO2Cl2. Okay. And the third point is 4f electrons have greater shielding effect when compared to 5f, and 5f or poor shielding effect. And in lanthanides, most of the ions are colorless, and in actinides, most of the ions are colored. Okay, and U3 plus is red in color, U4 plus is green in color, UO2 plus is yellow in color. Okay, and in lanthanides, most of them are paramagnetic and their magnetic properties are easily explained. And in actinides, they are also paramagnetic, but their magnetic properties are very difficult to interpret. Okay, and in lanthanides, they do not form complexes easily, and in actinides, they have much greater tendency to form complexes. And except chromium, all are non-radioactive. Chromium is the only metal is radioactive. Okay, and in actinides, all of them are radioactive. And in lanthanides, their compounds are less basic, and in actinides, their compounds are more basic. And in lanthanides, they do not form oxocations. In actinides, they form oxocations such as UO2 plus, UO plus, NPO2 plus, and then PuO2 plus. And now we are going to see the similarities between these two, that is lanthanides and actinides. The first one is they have common oxidation state as we saw plus 3, and then they involved in filling n minus 2 f orbitals, that is 4f and 5f. Okay, and then they are highly electropositive and very reactive nature. We saw in the properties of lanthanides and actinides. And then they both of them undergo lanthanide contraction and actinide contraction, that is a steady decrease in the atomic or ionic radius when increase in atomic number is known as the contraction. Okay, lanthanide means lanthanide contraction, actinide means actinide contraction, both of them are same. And then both show magnetic properties as we discussed in the differences. That is, in lanthanides, the magnetic properties are easily explained, but in actinides, the magnetic properties are very difficult to interpret. If you have any doubts, put it in the comment box. We will surely help you out. And thank you for watching.